All right, today we are talking about optimization. Okay, optimization is basically the process in which you are finding the maximum or minimum value of a function. Okay, so we're going to be able to use derivatives to optimize these particular functions. Now, today's notes are not mindless copying notes. You need to make sure that you guys are listening and paying attention, because a lot of the notes that are up here today are not just for you to sit there and fill in the blanks and then tune out for the rest of it. Okay, so make sure that you guys are paying attention. Also, with them changing the schedule with testing on Monday, you guys are not going to have your quiz on Fridays. Clearly, I don't see you on Friday, so it'll just be the test next Thursday. Does everybody understand that? So no quiz in between. We'll just go straight to the test. All right. We're going to spend 2 days on optimization so you guys understand what's actually going on. And yeah, any questions? No. The time there's no time for this. All right. So, like I said, optimization is the process of finding the maximum and minimum value of a function. Okay, that is the process. You use basically the first derivative to help you locate what your turning points are specifically. Okay, you use the first derivative to help you find your turning points. Your turning points are the things basically that indicate whether or not you have a maximum or a minimum value. Okay, now extrema don't always occur when you have a maximum or a minimum. Okay. And as we know, we can always figure out our extrema by doing what? How can we figure out our extrema? Solving the first derivative when it is equal to 0. Okay, that's how we can go about figuring out our extrema. Yes, we do know this. However, there is another test that you can use, the second derivative test, which can actually help us figure out our extrema. Okay. Also, one thing you also have to consider is that a lot of the other functions that we've dealt with, okay, they haven't been set on an interval, especially when we're doing graphing. We're looking at from negative infinity to infinity, right? However, if your domain is ever restricted, you also have to look at your endpoints as well, okay? If you look at this particular example, as you can see, this endpoint is higher than this point here, okay? So there's actually a maximum value that occurs at this particular x value, okay? And if you look here, well, this point is lower than this point, so this would be the lowest point on the graph, okay? So sometimes if the domain is restricted, you do also have to consider the endpoints to determine if it has a maximum or minimum located there, okay? Any questions on what I said so far? All right. So, to find optimal solutions, okay, there are 3 ways that you can do it. The first way is you can use your number line test, aka the first derivative, okay? We know how to do that. That's what we've been doing. We take the first derivative, set it equal to 0, we get a value. We put that value on the number line, and then we do test points to see if it's going from positive to negative or negative to positive. That way we can identify whether or not it has a local max or a local min. Okay? Any questions on first derivative? All right. The second derivative test, however, something that is new, all right, is also another way to help us determine whether or not we have a maximum or minimum value. What you do is after you find what the first derivative is, you set it equal to 0, and you find your values. Instead of making a number line, you take those points and plug them into the second derivative. Okay? When you plug it into the second derivative, if you get a value that's less than 0, then you know you're going to have this type of shape, which means you're going to have a local maximum. If you plug it in, you get a value that's greater than 0. It's going to be the upward shape, meaning that we have a local minimum. Okay? So you can use the first derivative test or the second derivative test to help you find your extrema. Will both tests work every single time? No, it won't work every single time. If you do the second derivative test and you plug in a value and it actually equals 0, you're not going to be able to use it. You're going to have to go back and use the number line. Okay? The number line, yes, the number line will always work. However, depending on the function, depending on the values that you get when you set the derivative equal to 0, it could be very time consuming, and it could be some not so nice numbers, making it a little bit more challenging. Okay? So the second derivative is there as another option. Okay? Questions? second derivative test. You can do that. Setting the first derivative equal to 0. Take those values and plug that into the second derivative. And then the last way, if you're allowed to use a calculator, you can always graph the function and then locate where the maximum and minimums are using the feature on the calculator. Okay? Those are 3 ways to optimize, to figure out your optimum solution. Okay? And what does optimize mean? What does it mean to optimize? Optimization? To find a maximum min of the function. Okay? And we're going to basically be dealing with these problems in the sense of like word problems. Okay? What is the maximum area for your garden if you have this much fencing? Or what is the minimum volume that you can sell for the biggest bang for your buck? Okay, you're going to be dealing with those types of problems. All right? What you see in your paper is the second derivative test, kind of outlined again. Okay? But basically, if you take the first derivative, set it equal to 0, and get your solutions. You plug those into the second derivative, there's the second derivative test. Those are those stipulations. You plug it in, you get a value that's less than 0.
Teachers at this time
Plug it in, you get a value that's less than 0, you have a max. If you plug it in, you get a value that's greater than 0, you have a min. And like I said before, if you plug it in, you get 0. You can't use the second derivative test. You will have to resort back to the first derivative test. Okay? So I have an example already worked out for you. It says to find the relative extrema for this function, 3x to the 5th minus 25x to the 3rd plus 60x plus 20, I think, plus 20. So basically, it's already worked out for you. If you flip it over, there's the work. The same thing that you see on the screen, same thing that's on your paper. The applied domain is all real numbers. There is no restriction, so no need to test any endpoints. Okay? You take the first derivative, set it equal to 0 to obtain possible extrema. Okay? So you take your function, the derivative of your function is set it equal to 0. If you notice, all terms have a 15 in common. You factor that out. This is a higher order quadratic that can still be factored. -4 and -1, x squared and x squared. These are difference of perfect squares. So you'll have 4 potential stationary points, okay? That's -2, -1, 1, as well as 2. Now, if you think about it, that number line, this will be the number line that you would have to use in order to do the first derivative test. That's 1, 2, 3, 4, 5. That's 5 regions, okay? And then that's a -1/2, a +1/2. I mean, you can still do it. You very much can still do it, but it's a time thing as well, okay? But what you can do is you can take the second derivative, which is this 60x to the 3rd minus 150x, which can be factored here, and then you can plug in each one of those values, all right? And it's not so much knowing what the number is, it's more about knowing whether or not it's a negative or a positive, okay? Because if it is a negative, that means it's less than 0, which means you have a relative maximum at s equals -2. Plug in -1, you get a positive number, meaning that you have a relative minimum, and so on and so forth. Okay? So that can save you a little bit of time there instead of having to plug this into this particular type of function and then going from there. Questions? Then you guys give it a try. Okay? I want you to find any relative extrema using the second derivative test. You have the function x to the 3rd minus 12x. I want you to determine any relative extrema using the second derivative test.
Teachers, once again.
So you figured out that in positive 2, you had a what? You had a min. And at negative 2, you had a what? You had a max. Okay? So then what are those points? Because remember, maxes and mins, these relative maxes and mins are absolute maxes and mins. They are points. Okay? Don't leave anything to chance. How do you figure out those y values? Plug what you got into the original. So let's do that quick. Plug in positive 2. And you get negative 16. Plug in negative 2. Remember, whenever you raise it to a odd power, you are multiplying by itself that number of times. Plug in negative 2, you get what? Positive 16. So here's where your relative, both of these are relative, they're not in points, so there's not absolute. They're both relative mins and relative maxes. Uses your number line to determine that as well, correct? Okay? If you did the number line, that is the first derivative test. So that is a negative 2, positive 2. Test points you can plug in. And you're plugging them into your first derivative. When you plug in negative 3, did you get a positive or a negative? When you plug in 0, positive or negative? When you plug in positive 3, you got a positive. So that basically lets us know that we're going from positive to negative, negative to positive. A max and a min. Okay? Same thing. But like I said, depending on the problem, it might be easier to use one over the other. It might also be a time saver to do one over the other. Questions on using the second derivative test? So, your steps to optimizing a problem. The first step, does it hurt to draw a diagram? Sometimes it might be easier to see exactly what you're dealing with. Okay? Step 2, you want to construct a formula to be optimized. The problem will always tell you what you're trying to find the maximum of, what you're trying to find the minimum of. So say maximum volume, minimum area, maximum cost, minimum profit. Okay? That kind of lets you know what equation you should be taking the derivative of. Alright? Which basically means you need to know probably some old school formulas. Alright? Such as volume and surface area. Those are the two big ones that students tend to forget, because everybody remembers what the area of a rectangle is, correct? What's the formula? Length times width, or? Base times height. Okay? And everybody knows what the area of a triangle is, correct? What is it? 1/2 base times height. You're thinking, oh, our reference book should have these things. Are you sure? Anybody have their reference book? Pull it out. Let's see what formulas you do need to know versus the ones you don't need to know. If you don't have your reference book with you, maybe a neighbor can kind of say, hey, you don't have to worry about these. I got you, friend. My reference book is right here. So your reference book gives you your volume formulas, right? And some of your area ones as well, but they do not give you any of your, none of your surface areas, okay? So let's kind of go back and review from those good old geometry days what those formulas are. Does anybody remember potentially the surface area of any of these shapes? Yes? One person? What does surface area mean? The area of the surfaces. Okay? So if you think about a cylinder, everybody knows what a cylinder looks like, right? If you ever had a can of anything in your life, you've seen a cylinder. Okay? A cylinder is comprised of what? What shapes? 2 circles and a rectangle. What's the area for a circle? Pi r squared. So and how many circles do you have in a cylinder? 2. So you have 2 pi r squared, which represents the 2 circles. Now what do you get to represent that rectangle that kind of goes around the middle part? Yeah, so it's basically the circumference times the height. Circumference is pi d or 2 pi r, and then you multiply by your height. So you can say pi d times h or 2 pi r h, either one. And actually, I want to write this one using my r's, because later it'll be helpful to have not 3 variables, but 2. What about a cone? Anybody remember a cone? It does have a circle, which means that one part of the formula is pi r squared. Then you got to represent that top part. When you unravel it, it doesn't really look like a rectangle. Something else. One half of close. You're right on the 1/2 part. You're right on the circumference part, but it's not the height. Because if you think about a cone. Oh. I think this is a cone. Make sure. This technically is your height. We don't use that. We use something else. Another piece. The slant height. So it's actually your slant height. So it's going to be pi r l. And when you took half the circumference, which is 2 pi r, when you took half, that's what happened to the 2. What else is on there? Sphere. What about sphere?
It's a circle in 3 dimensions.
It's a circle in 3 dimensions. That is true. I actually mentioned it at one point in time in this class. I don't know if anybody ever caught that.
Do you know what's like the only thing that you would be 360 pi r squared, but no, that's not right.
There's a pi r squared in there. It is 4 pi r squared. It is 4 pi r squared. That is surface area of a sphere. What about prism? What about prism? You just what?
It's like 2 base times height. And then like 2, it's like 2 of each like range of height. So it's like 2 L times W, 2 W times H, and 2 L times H.
Exactly. Okay? Basically, you're taking the area of all of the sides. So basically, the area of the two, the left and the right, the top and the bottom, the front and the back. Okay, you take the area of basically all of those. But then, what happens when it is not a rectangular prism? What if it's a triangular prism? Or a pentagonal prism? Find the area of each side. Okay? So, what happens when you are presented with like a triangle or a pentagon or something? And then you add them together. Okay, so the triangles represent the what of the prism? The bases, right? So you can find the area of the bases, and how many bases are there going to be? 2, and then you find the area of the however many sides you have. This pentagon, you have 5. This triangle, you'll have 3, etc., etc. In general, the one that Sarah gave us, yes, that works for all rectangular prisms. In general, this is your formula. 2 times the area of your bases plus the perimeter of your base times your height. That will give you the 2 bases and then the sides. So once you find the formula that you're going to be optimizing, you want to take the first derivative and find the value that makes that variable 0. And then after you do that, if there are any restricted domains, you want to make sure that when you perform the first derivative test or the second derivative test, you make sure that you also include endpoints as well. But basically, step 4 is when you determine whether or not you have a maximum or a minimum. And that's where you either are going to use the first derivative test or the second derivative test. Now step 5, a lot of times step 5 is optional, but it depends on what the question is asking. If it ever says to justify your answer, does this answer make sense? Anything of that nature, that you want to make sure that you write a sentence explaining why the solution isn't works, why it makes sense. Okay? But let's be realistic here. If I'm trying to figure out the dimensions of a cube or something like that, and one of my values is a negative, is that possible? No, it's not. You can't have negative dimensions. Okay? And also think of it, if you only have a certain amount of fencing to put around a yard, and one of your answers is like outside of the potential amount you can use, then you're not going to use that as well. Okay, so you have to, think smarter, not harder. So we're going to look at some examples. We're going to do 3 together, and the rest are going to be on you. Okay? A rectangular cake dish is made by cutting out squares from corners of a 25 centimeter by 40 centimeter rectangle of the 10 plates, and then folding the metal to form a container. What size squares must be cut out to produce the cake dish of maximum volume? And I put this here because, like I said, in the past 3 years that I've taught SL, I've never been here for this lesson for whatever reason. Okay? Bless you. Bless you. All right. So this here was just me explaining to those who are working on these problems. Key word, maximum volume. So the formula that you're going to be taking the derivative of needs to be what? So step 2, where it says construct a formula to be optimized, what formula are we going to be taking the derivative of? Huh?
Volume.
It's going to be volume, because it says to find maximum volume. Remember, optimization is finding the maximum or minimum of a function. Maximizing volume lets you know that you're going to be taking the derivative of the volume equation that you come up with. Okay? So I'm telling you, it always tells you what equation you're going to be creating. It's just a matter of creating that equation. Okay? So, step 1 says what? Let's draw a diagram. Because right now, does anybody have an idea of what this could potentially look like? Right now, if you have no idea what this could potentially look like. When it says you have a rectangle and you're cutting out sides to form a cake dish. Okay, so draw a picture. It's being formed from a rectangular cake dish that's by 25 centimeters by 40 centimeters. So I need a rectangle. And we're cutting out squares from the corners. If you cut out squares from the corners, right, that means you're cutting here up, cutting out corners. And they gotta be squares, right? And if they're squares, that means that each of these cuts are going to be what? They're going to be equal. Now, do we know how much we're cutting? No, so we're going to label this. We're going to label this X. So when you cut those corners and you fold, you're going to end up creating this a 3-dimensional shape. Okay? Now, what are my dimensions? 25 by 40, original. But if I cut off, these corners, what are my dimensions now? 25 minus 2x, because I cut an x from this side as well as that side. And then 40 minus 2x. Okay? And when I cut them out and I fold it up to create my little 10 here, I've created what type of shape? A cylinder. A prism, basically. So, when we're trying to figure out the maximum volume, the equation that I'm going to need to use is the volume equation for a prism. What is that? What is the formula for the volume of a prism? Length times width times height. What's my length in this problem?
25 minus 2x.
25 minus 2x. What's my width?
40 minus 2x.
And what's my height? X. Because however much I cut off, when I fold it up, those are going to represent the size of it. Okay?
So you said x is 4.
Say it.
You folded the x.
Yes. So basically, when we cut off these edges and we like make your folds, the height of this dish is going to basically be this height here. However much that is. And that's what we're trying to figure out. All right? So there's your equation. It's all in the same variable. There's no extra variable here. So to take the derivative is actually going to be pretty simple. What do I suggest that you probably might want to do first? FOIL. Distribute. Don't try to do product. Don't. Stop. Don't do that. Okay? Multiply this out. Get your normal volume equation. Then take the derivative. Okay? So, go ahead and do that. Give me my normal volume equation. Once we distribute, FOIL, distribute, we should have the volume equation that is 4x to the third
minus 130x squared.
Did everybody get this? Okay. So now we are trying to now we're good to go. Now we can go on to step 3, which says find the first derivative, set it equal to 0, and then determine our maxes and our mins. Okay? So go ahead and do that. You're going to find the derivative, set it equal to 0, find my solutions, and then using one of the two tests, either first derivative or second derivative, to determine whether or not, or which value gives us the max. You guys try to factor. Just find a GCF first. What's the GCF? 4. Okay. We take out 4 from this, you get a 65. And a 4 from this, you get a 250. Still gonna have to use California. 3 times 250 is 750. The two numbers multiply to give you a positive 750, but add together to give you a negative 65. Not be positive. Be positive. And 50. Okay, and they're going to have to be negative in order for you to get that negative 65. So, does that reduce?
Yes.
To what? X minus 5 and the other one? 3x minus 50. So you set both of these equal to 0 and you'll get x equals and 50 over 3. Okay? Now, before you start going into the whole process of trying to do the number line or anything else like that, or the second derivative test, could any potential number work here that you could plug in for x? Or is there a restriction on exactly what the height could be before I not even have a 10? Yes? You said I can't or can't? You cannot. Why can I not plug in 50 over 3?
Because 50 over 3 is going to be greater than half of 25, which is one of your side lengths.
Mm-hmm.
And since you're cutting out each corner,
Right. So, because 25, that is your smallest length, right? You can't plug in anything that's going to be bigger than potentially half of this, okay? And if you're like, well, how do you know it's half and not a third or something like that? Then just set this side equal to 0. That will also give you your solution as well, give you the largest value that you could potentially plug in, okay? So 12 over 5 is the largest value that we could potentially plug in, and 50 over 3 is very much larger than that. So we basically only have to test 5, okay? Now 5, we can do either way. You want to do second derivative, you want to do first derivative test, which one do you want to do? Second derivative? Okay. So then that means I need a second derivative. What's my second derivative? Oh, wait, that's the original. Here. What's my second derivative? Anybody? 24x minus 260. So if I plug in 5, does that give me a positive number or does it give me a negative number? It's going to give me a negative number, which means that's less than 0. Which means by the second derivative test, if your value is less than 0, that means you have a max. So we're basically confirming that yes, we do indeed have a max because the second derivative is less than 0. So it says, what size squares was we cut out to produce a cake dish of maximum value? The size is going to be 5 centimeters. I know I'm kind of all over the place because I don't have the space, but you guys hopefully have space in your paper. So you're going to be taking the derivative of the surface area and finding where there's a minimum. Okay, that's steps 3, 4, and 5. Now we have to figure out what type of shape is going to be this, okay? Now think about it. What shape could potentially have a square base and vertical sides with an open top? We are looking at a box like a cube or a box in the sense of like a rectangular prism, one that doesn't have all equal sides, right? It couldn't be a pyramid. Oh, that's one I did. Couldn't be a cone or a cylinder because one we have a square base, okay? And on top of that, it says a 4-liter container. 4 liters. 4 liters is referencing what? The volume. Okay? It's representing the volume. Okay? So we basically have some type of prism, whether it's a cube or rectangular one. So that's our picture that we're drawing. Has an open top. Okay? If it has a square base, then that means we know that the dimensions of the base are what?
Equal.
They're equal. So we're going to label them both x. And right now we don't know if it's going to be x on all 3 dimensions or if it's going to be, the height is going to be something different. Okay? So just for right now, we're just going to label it as an h because that's what we're trying to figure out. We're trying to figure out which shape is going to be the most economical shape. So it's really going to be the matter of the height. It's going to tell us that. Okay? And the 4 liters represents volume. Now, there is a conversion that I wonder if anybody remembers. So right now, we really don't know what units we're dealing with, correct? Liters really talks about volume. But there is a conversion that can let us know that it's from liters to something. Anybody know that conversion? Huh? Potentially. Potentially. It could help you. Does anybody know the conversion from liters into, what'd you say, Caleb? Into centimeters. Anybody know that conversion? So then that means 1 liter would equal what? I don't know if anybody heard them on this side, okay? So I'm going to write it. 1 liter, if you didn't know, equals 1,000 centimeters cubed. Which means that 4 liters would be what? 4,000. You needed to know this in order to even start really this problem. Okay? So if you did not know that, now you know. Okay? So that 4,000 centimeters represents volume. And since this is a prism, or potentially a cube, what is the volume of the cube? What's the formula? Length times width times height. But we already know that the length and the width are both. So we'll do x times h, or nicely written as what? X times x. Okay. All right. Now we do have to use this to help us. I know we're trying to minimize surface area. What's the equation for surface area of a prism? You have 2x squared. The x squared represents the area of your base. So that's the 2b part. And then pH is perimeter of your base times your height. Since your base is all x's, that's x plus x plus x plus x, which is a 4x. Okay? Now, we just can't start taking the derivative of our surface area because of what reason? You got two variables. You got an h in there. But we can use this equation that we created for volume to solve for one of your variables and plug in. You cannot take the derivative in this class, you do not take the derivative when you have two different variables. You can, but that's not for this class. So in order to take the derivative, you have to have the same variable all the way through. So what you do is you use this other equation that we've created using the volume to solve for that variable. And then we're going to plug in. The easiest variable to solve for clearly is going to be what? H. How do I solve for H? Divide by what? X squared. And then this is what you plug into this H. Can you guys go ahead and simplify that for me? So your surface area equation is 2x squared plus 16,000 over x. That is the equation that you're going to end up taking the derivative of and setting equal to 0. Okay? Questions before I let you go to figure that out? All right. Find the derivative. Set equal to 0. Get my solutions. Okay, so you have to take the derivative of this function. The derivative is a 4x. Hopefully you brought this up so that it was x to the negative 1. Did you guys do that? So then it would have been a negative 16,000 x to the negative 2, which basically simplifies down to be negative 16,000 over x squared. Did you guys get that?
Yeah.
Then you set this equal to 0. When you do, you'll end up subtracting over 4x. Because you got, right? Did you guys do that?
Yeah.
Okay. When you subtract over, this will give you a negative 4x. But because you have a negative on the left and a negative on the right, they both become positive. Did everybody see that?
Okay.
Okay? So then from there, you'll multiply both sides by x squared. Correct? Don't you want to get rid of the denominator?
Yeah.
So then this will be 16,000 equals 4x to the third. Divide both sides by 4. And what is that? 4,000? Okay. Something's wrong. It's supposed to be 8,000. This was an open top box, which means that when we did surface area, which was 2B plus pH,
It's just one.
it's just 1B. Okay? So our equation should not have a 2 here. Okay? Which means that when we took the derivative of x squared, we should have gotten a 2x. Which means that when we subtract it over, we should have subtracted over a 2x, and then that becomes a positive. So this will be a 2x to the third. When we divide, that'll give you an 8,000. So that way, when you take the cube root, you get the cube root of 800 is 20. Okay. So this should have been the original surface area. It should have been x squared plus 16,000 over x. The derivative would have been a 2x minus 16,000 over x squared. Subtract 2x from both sides. Turn them both positive because both of them would have been negative. Multiply both sides by x squared. Divide 16,000 by 2 to get 8,000, and then take the cube root. If you're unsure what the cube root of 8,000 is, what's the cube root of 8? What's the cube root of 1,000? Multiply them together. Do you want to do the number line, or do you want to do second derivative? Okay. All right. If we do the second derivative, that would have been a 2 plus 16,000 times 3 is, times 2 is, it'd be 32,000 all over an x to the third. Ignore this extended line here. So when you plug in 20, are you going to get a positive or are you going to get a negative? You're going to get a positive, okay? So the second derivative with 20 gives you a positive number, which means that this is indeed it is indeed a min, okay? Now 20 is not our answer. The question was asking us what's the most economical shape. So if x is 20, this is 20, this is 20, and our height is going to be what? What's 20 squared? What's 4,000 divided by 400? It's 10. Is this a cube? No, it's just going to be a what? It's going to be a person. Not a cube. And it's not a cube because all the sides are not the same. All right, the last one, I'm going to draw in a picture. You also have to add in this right here beside the AC. So here's the picture that goes along with it. Here's step one. I'll help you out there. I'll also run out of time a little bit. It says the animal enclosure is a right angle triangle with one side being a drain. The farmer has 300 meters of fencing available for the other two sides, AB and BC. If AB equals X, then show that AC is that right there. It's a show problem, which means it's the algebraic processes. Okay? If you have 300 meters of fencing that's available for the other two sides, then what's BC? 300 minus X. And you're going to use that information to help you find AC. How are you going to find AC? Pythagorean. I did the theorem. Pythagorean theorem. Which says what? A squared plus B squared equals C squared. A is either of the two sides, AB or AC. Doesn't matter. But what matters is C. C is always the hypotenuse, which we just figured out was 300 minus X. What's going to need to happen to that right side? You got to FOIL it. Go ahead and FOIL it. Go ahead and FOIL it. And show that AC equals the square root of 90,000 minus 600x. Go ahead and do that. Did you guys get this so far? Yes, you FOILed to get 90,000 minus 600x minus x squared. Then did you, plus x squared, did you subtract an x squared over to cancel it out? And then how do you get AC by itself? You got to take the square root. So then that is how you get questions on this. Now we have to find the maximum possible area of the rectangular enclosure. I don't give you any hints this time, but what is going to be the formula we need to construct that we're going to take the derivative of? 1/2 base times height. What's the base? The AC, and what's the height? X. It's never the hypotenuse when you're looking at a right triangle. So the equation for the area is going to be 1/2 X times all of that. Do we have the same variable? We do. So we don't have to worry about trying to figure out something else out. So now we need to take the derivative of it. To take the derivative, we're going to need to use what? Product. And chain. A good little review right here. Okay? So I'll give you guys about 4 minutes to work this out. Product and chain. Just the derivative before I check in. All right, so make sure that you take a look at the attachment that I have so that way you can see the math that goes along with it because I'm having some pen issues. So I'm just going to write it out and then I'm going to attach it as